This here we have a quadratic equation. It has two roots, x equals to 2 and x equals to 3.
What is a root?
When we factorize this, we get x minus 2 times x minus 3 equals to 0. When we put either of these two values, the function becomes 0. This proves any polynomial which has greatest power of x as n has n roots. When we plot a graph for this equation, y equals to x square minus 5x plus 6, the graph looks something like this. This point has coordinates 2, 0 and this point has coordinates 3, 0. That means our roots are the points where our graph intersects the x-axis. Let's do it for one more quadratic equation. X square minus 4x plus 4 equals to 0. This has the roots x equals to 2 and x equals to 2.
So you say there are two common roots for the same quadratic equation?
Yes, when we factorize this we get x minus 2 the whole square. That means this function here is a perfect square. When we plot a graph for this, we get this point here has coordinates 2, 0.
But it intersects the x-axis only once.
It touches x-axis, but we shall prove it has two roots. To prove this, we shall introduce a new operator called differentiation. It's represented by dy by dx. This here means a very small change in y with respect to a very small change in x. This gives slope of each and every point of a function. Let's assume our function is y equals to k x to the power n, where k is a constant x and which has the power n. When we differentiate it, we get our k remains the same, our power here comes out times n x, and we subtract 1 from the power x minus 1, and differentiation of a constant y equals to k dy by dx equals to 0. Now our function was x square minus 4x plus 4 equals to y. Let's differentiate this. Here for differentiation of x square, the 2 comes out, it becomes 2x, 2 minus 1 minus 4, the constant comes out, x 1 minus 1, and differentiation of a constant is 0 equals to dy by dx. Let's plot a graph for this function. This point here is 2, 0. Now let's plot a graph for this function. 2x minus 4 equals to dy by dx. We see this is a straight line passing through 2, 0. Now let's understand the meaning of this graph. This y-axis represents dy by dx. Every point here represents the slope of the corresponding point here. That means the slope here, the coordinate on this y-axis represents the slope here, where the part of this graph is above the x-axis. That means our function is positive. This function here has positive slope. That means our function is increasing with time. The part where it is below the x-axis, our function here is decreasing. But there is a very special point here where it intersects the x-axis. Here the slope itself is 0. Now let's understand what do you mean by slope itself being 0. That means our function at 2, 0 is a straight line. When we enlarge this function infinitesimally, we get it reaches the x-axis, and because at 2, 0 and because the differentiation shows that the slope is 0, it becomes a straight line and then again rises. That means at this exact one point 2, 0, it becomes a straight line and intersects the x-axis twice.
So what about a cubic equation having 3 roots?
Okay, we can take a simple cubic equation. X cube equals to 0. It has 3 roots. Because the power of x is 3. X equals to 0, x equals to 0 and x equals to 0. When we plot a graph for this function, we get here it has the coordinates is 0, 0. When we differentiate it, dy by dx, the power comes out 3x. Subtract 1 from the power, we get 3x squared. Now let's plot a graph for this function. This is a parabola touching the x-axis at 0, 0. We had just now proved that a parabola touching the x-axis, which is a perfect square, that means cuts it twice. That means here it cuts the x-axis twice. That means the slope at 2 instances of this function is 0. So when we enlarge this infinitesimally, we get our function comes up. Here it reaches the x-axis, it becomes a straight line, it again becomes a straight line, and then it rises. This whole thing is a single point, 0, 0. We have just enlarged it for our convenience. This proves that a perfect cubic equation cuts the x-axis thrice. Now let's take a cubic equation which is not a perfect cube. X cube minus 1 equals to 0. It has the roots x equals to 1, x equals to omega and x equals to omega square. These two are the imaginary roots. Now let's prove why it has only one real root. When we plot a graph, we get something like this. This point be 1, 0. Now let's differentiate this function. Dy by dx is equals to, the power comes out 3x, 3 minus 1, and differentiation of a constant is 0. That means our dy by dx is again 3x square. Now let's plot a graph for this function. Dy by dx, we see that it touches the x-axis at 0, 0. That means the slope at x equals to 0 is 0. So here our function becomes straight line twice. But here x equals to 1, it has the coordinates x equals to 1 and y equals to 3. That means here the slope is 3, not 0. Therefore, it cuts the x-axis once. That is why we have only one real root and two imaginary roots.